The world of computers has undergone a mind-boggling transformation. We've gone from simple 8-bit processors like the MOS 6502 to the behemoths of today, boasting billions of transistors. The MOS 6502, the heart of machines like the Commodore 64 and Atari, was a marvel of its time. It brought gaming and computing to the masses. Fast forward to the present, and we have CPUs like AMD's EPYC Rome. This monster packs an incredible 32 billion transistors onto a single chip. The sheer scale of this difference is hard to fathom. Imagine comparing a model airplane to a jumbo jet. Both fly, but the complexity and capability are on entirely different levels. The 6502, with its 3,510 transistors, was a masterpiece of efficiency. It squeezed every ounce of power from its limited resources. Modern CPUs, with their massive transistor budgets, can perform feats unimaginable just a few decades ago. This incredible leap in technology has revolutionized what we can do with computers. From complex scientific simulations to stunningly realistic video games, the possibilities seem endless. But amidst this technological whirlwind, there's a certain charm to the simplicity and elegance of those early processors. The 6502, with its straightforward architecture and limited resources, fostered a generation of programmers who could squeeze every last drop of performance from the hardware. This nostalgic yearning for the simplicity of the past has led some to wonder, what if we could bridge the gap between these two worlds? What if we could take the elegance of the 6502 and marry it with the power of modern technology? Could we build a 64-bit MOS 6510 compatible CPU using today's manufacturing processes? Let's delve into this intriguing possibility. The idea of a 64-bit MOS 6510 might seem like an oxymoron. After all, the 6502 family was designed in an era where 8 bits was the norm. But with modern fabrication techniques, we can pack billions of transistors onto a chip. This opens up exciting possibilities. Imagine a CPU that retains the simplicity and elegance of the 6510 instruction set. It would be familiar to those who cut their teeth on 8-bit machines. But now, imagine it with the power and address space of a 64-bit architecture. This isn't about simply creating a more powerful 6502. It's about exploring a unique blend of the old and the new. Such a processor could unlock a treasure trove of retro software. Imagine running classic games and applications with the benefits of modern hardware. Increased speed, vast amounts of RAM, and advanced graphical capabilities would breathe new life into beloved classics. Of course, creating a physical 64-bit MOS 6510 comes with its share of challenges. The original chip's design would need significant modifications to accommodate the larger address space and data paths. There are also questions of compatibility. How do you maintain the spirit of the original architecture while incorporating modern features? While a physical chip is a fascinating concept, there's a more accessible route to explore emulation. Emulators have long been used to recreate the experience of older systems on modern hardware. Could we leverage emulation to explore the possibilities of a 64-bit MOS 6510? Emulation offers a powerful tool for exploring the potential of a 64-bit MOS 6510. Instead of fabricating a physical chip, we can use software to mimic its behavior on existing hardware. This approach allows for greater flexibility and experimentation. We can tweak the design and capabilities of our virtual CPU without the constraints of physical manufacturing. Emulators work by interpreting the original CPU's instructions and data. They then translate them into operations that the host computer can understand. This process, while complex, allows us to run software designed for one system on a completely different one. To create our 64-bit MOS 6510 emulator, we'd start with an existing 6502 emulator as a foundation. Then we'd modify it to handle the larger address space and data paths of a 64-bit architecture. This would involve rewriting significant portions of the emulator's core. It's a daunting task, but the potential rewards are immense. Imagine playing classic Commodore 64 games with enhanced graphics, smoother gameplay, and even online multiplayer capabilities. Emulation isn't just about recreating the past, it's about breathing new life into it. When it comes to building a robust and efficient emulator, the choice of programming language matters. Free Basic, with its roots in the BASIC language familiar to many retro enthusiasts, offers an excellent option. It provides a familiar syntax and structure. This makes it easier for developers to grasp the concepts and dive into emulator development. But don't let its basic heritage fool you. Free Basic is a powerful compiled language capable of handling the complexities of emulation. It allows for direct memory access, a crucial feature for manipulating the virtual memory space of our emulated 64-bit MOS 6510. Free Basic also excels in its ability to interface with low-level system components. This is essential for tasks like handling input from the keyboard, mouse, and joysticks, as well as outputting audio and video. Furthermore, its active community and extensive documentation provide valuable resources for both novice and experienced programmers. This ensures that we have ample support as we delve into the intricacies of building our 64-bit emulator. Section 5. The Power of Light, POV-Ray and Ray Tracing for Retro Graphics. One of the most exciting prospects of a 64-bit MOS 6510 emulator is the potential for vastly improved graphics. While the original 6502 struggled to produce even simple sprites, our emulator can harness the power of modern GPUs to render stunning visuals. This is where POV-Ray comes in. POV-Ray is a powerful ray tracing program. It simulates the behavior of light to create photorealistic images. By integrating POV-Ray into our emulator, we can render the simple shapes and sprites of classic games with incredible detail. Imagine the iconic sprites of Space Invaders, but now with realistic lighting, reflections, and even shadows. Ray tracing allows us to achieve a level of visual fidelity that was simply unimaginable in the 8-bit era. Of course, integrating POV-Ray into a real-time emulator presents its own set of challenges. Ray tracing is computationally expensive, and we need to find ways to maintain smooth performance. This might involve optimizing the ray tracing code, utilizing the GPU's parallel processing capabilities, or even exploring hybrid rendering techniques. Section 6. Pixels and Shaders, GLSL for Enhanced Visuals. While ray tracing offers a path to photorealism, it's not the only way to enhance the visuals of our 64-bit MOS 6510 emulator. We can also leverage the power of shaders to create a variety of graphical effects. Shaders are small programs that run directly on the GPU. They allow us to manipulate individual pixels in real time. GLSL, the OpenGL shading language, provides a flexible and powerful way to write these shaders. With GLSL, we can create shaders that mimic the look of classic CRT monitors, complete with scan lines, phosphor glow, and even subtle color fringing. We can also use shaders to implement more advanced effects like bloom, depth of field, and ambient occlusion. These effects can add a level of depth and atmosphere to classic games, making them feel more immersive and engaging. The possibilities are truly endless. We can even create shaders that introduce entirely new graphical styles, while still maintaining the spirit of the original 8-bit aesthetics. Section 7. Overcoming the Hurdles, Challenges, and Solutions. Building a 64-bit MOS 6510 emulator, even through software emulation, presents its fair share of challenges. One of the primary hurdles is balancing accuracy with performance. Emulating every nuance of the original CPU's behavior, while also running modern enhancements, can be computationally demanding. We need to find clever ways to optimize our code and utilize the host computer's resources efficiently. Another challenge lies in handling the vast address space of a 64-bit architecture. The original 6502 was limited to 64 kilobytes of memory. Our emulator needs to manage significantly larger amounts of memory without sacrificing speed. This requires careful memory management techniques and potentially even utilizing virtual memory. Furthermore, ensuring compatibility with existing 6502 software while introducing new features can be tricky. We need to strike a balance between preserving the original software's behavior and taking advantage of the expanded capabilities of our 64-bit environment. Overcoming these challenges requires a deep understanding of both the original 6502 architecture and modern software development techniques. It's a testament to the ingenuity and dedication of the emulation community. Section 8. A new era of retro computing applications and implications. The development of a 64-bit MOS 6510 emulator opens up a world of possibilities for retro computing enthusiasts and beyond. Imagine a future where classic games can be experienced with enhanced graphics, smoother gameplay, and even online multiplayer capabilities. The educational potential is also immense. Such an emulator could serve as a powerful tool for teaching computer science principles. Students could learn about computer architecture, assembly language programming, and the history of computing in an engaging and interactive way. Furthermore, the ability to run legacy software on modern hardware has practical applications. There are countless industries and organizations that still rely on older software. Our emulator could provide a way to keep these systems running smoothly on modern hardware, ensuring continued functionality and preserving valuable data. Section 9. Conclusion: the future of the past. The journey from the humble MOS 6502 to the concept of a 64-bit counterpart is a testament to the enduring legacy of early computing. While a physical 64-bit MOS 6510 might remain a fascinating thought experiment, emulation provides a tangible path to explore its potential. By harnessing the power of modern hardware and software, we can breathe new life into classic games and applications. We can create unique educational tools and even find practical solutions for running legacy software. The future of retro computing is bright. It's a future where the past and the present intertwine, where the simplicity of yesterday meets the power of today. It's a future where the spirit of innovation that fueled the 8-bit era lives on, inspiring new generations of programmers and enthusiasts.